Um, okay, so today we're going to talk about a kind of like very exciting project at this time, in which we try to use multimodal learning to do a simple classification task, but that is still very hard to predict with normal methods. And at the end, I'm going to talk about a little bit about like next steps and like things that might be useful from the CS perspective to inform like new models or new ideas in chemistry and physics. Um, so this project is done with my advisor, Marshall Burke, an economist, Jeff Wen, who decided to make money in Tesla, and two economists, Jod and Pat. Patrick, I guess Tina, you can talk with Patrick. He's interested in like pollution and wildfires, and he's in the econ department at UBC. We don't know sometimes why houses burn during wildfires, so we have like a gross understanding of amber transfer might be related to it, but sometimes you have these scenes where like complete neighborhoods are devastated and there is this only house that survived. So weather is of course very relevant in this, and we know from some causal evidence that building codes enacted during the mid 90s in California reduced fire damages by some amount. The Cal Fire policy, and this is what is suggested to be followed in California in the wildlife urban interface, is that we need to have a defensible space. This defensible space, these are meters, are asking you to remove like vegetation on like vegetation and different kind of fuels in these like buffers around your house. Um, what we want to see here is we want to classify households with aerial imagery and see if we can like predict if these houses are going to burn or not. There's like two main ways in which you can approach these prediction tasks. On one end, you can only use like vision-only models in which you can pre-train these vision architectures or fine-tune them to new tasks. On the other hand, and this is what we see a lot on like the ML that we do in our group to understand PM, we use tree-based models in which we try to featureize images. Like if we have like images or weather data or whatever, we featureize it into a table, kind of like a tabular format, and we make predictions on that. So one of the good things of using vision models is that we can use state-of-the-art models. We can fine-tune them or adapt them to different downstream tasks. This is not only classification, can be regression, can be generation, or whatever other task you have in mind. It can be like a self-supervised model or whatever. But a problem with this is that when you don't have vision data, it's hard to pass that information to the model. So if you have like something that it comes only in text, like the value of the household or other things, they're completely going to be forgoed by the model, and they're very hard to encode as vision features. On the other hand, we have like these auto models that are tabular. They're very easy to implement. You can like feature whatever. If you can put it on a table, you can put it there. So you can put many data modes. But the problem is that it misses the spatial context. So, I'm not gonna bitch on my own research that of my lab, but like you can see that a lot of these PM predictions that Marshall and others have generated, they have like these kind of like artifacts on the data in which you can see the grids from the reanalysis and things like that. And all of that comes from the fact that a lot of these models are unable to understand a space and how like one thing is related to the other one. So it's very common to see these like artifacts when you train random forests with the spatial data. And at the same time, they completely lack expression. So sometimes if you want to see like linear relationships in these relationships or like more like or like deep relationships, they're like hard to grasp from this. So the approach we're taking here is combining the two of them. And the way we do this is by using foundation models. I guess I don't have to introduce what a foundation model is here, but basically it's taking a bunch of data and using different learning architectures to adapt this, to have like a general model that can be adapted to different tasks. So I think the most common of these foundation models, so like they're able to do this emerge and homogenization. That's kind of like the feature of them, and it's basically this idea of adapting to different tasks. You have seen these foundation models. Maybe you use them in your code, or if you want to ask questions about life to any of this. They're not only chat related. There is also generation, like the Lee. There's like Clip. If you use Instagram, Clip is in your lives, or like other models that actually are weather related that we're gonna talk later about. We're gonna talk about Clip today. That's gonna be like the way we're gonna combine these two things. So basically, imagine you can have, what we want to do here is like we want to basically join text and image representations. So imagine you have like a tuple of these two. These are images that are coming from aerial imagery surveys in California, and you have like text prompts, and these text prompts are going to come from like ourselves. Like we collected a bunch of data about like weather and whatnot, and also about characteristics of the house, and we're going to create like a cute prompt for each of these house. So your input data is going to be these tuples, and what we're going to do and what it's powerful about this is that we're going to basically encode information from both text and image into different vectors. So these are going to basically summarize my images, and it's going to summarize my text, and it's going to put it in an embedding space that is common between the two of them. So we don't have this problem anymore of like, oh, images and text not talking to each other. Now we're going to force them to talk to each other. And for this, we're going to create this like multimodal embedding space. And this is what Clip is doing. Basically, it's bringing these two things together. And this is going to be a huge sparse matrix in which, like, I don't know, a house made out of clay is not going to talk with like a description that is not aligning with that. So you're going to have a 0 there. But if that clay is like related to something else in my text, then it's going to activate. And this is what we're going to play around here. And this is going to be our new input, and this is where we're going to do classifications on top of. Okay, so as I was saying before, we have these images that are 60 meter per pixel, and we are going to use tabular data, which is using GridMed and a bunch of other house features that we got from private vendors. We have a little bit of a problem here in which we have only a few, we have like some imbalance in the labels. So we use like classic ML tricks to deal with this, mainly just like changing the loss function. So it upsample, it like gives more weight to some of these weights. And we're gonna take the tabular data and we're gonna transform it into different text prompts. So how we decided these text prompts, we experimented with different text prompts, and these are the ones that gave us more accuracy at the end. And basically it's just like literally just taking a row of these text and say like, okay, like these unburned house, like we're giving it the label, it did this and did that, and like the wind blowed at this speed, and it had like so many rooms, and like it cost like this amount. That's kind of like the information we're giving to it. And then what we have at the end is that we use this data to have like this huge matrix, and then we're going to start asking questions to that matrix. And the way we do that is using this fancy thing called a fine-tuned feature learner, in which I'm going to give the model the same image, but 2 different prompts. And the only difference in the prompt is going to be the label. So I'm gonna ask kind of like this oracle sort of like, what do you think? Is this burned or not burned? And at the end, what the model is gonna do is like it's gonna calculate distances between the input that I'm giving it, and it's gonna tell me what is gonna be the end result of this after the fine tune. So it's gonna tell me like this is like the second part in which like I run the softmax over like whatever the model is giving me, which is literally just taking the row and column of that. And I'm gonna say like, you know, is the model the model is gonna tell me, is this an unburned or a burned house? So it's gonna give me a probability at the end. To create embeddings, and this is where the secret sauce is, we need like very good models to be able to summarize our image and our text. So the better our model is, the better these embeddings are going to be, and the better they're going to represent the real data. So to do that, we're going to use BIT, which is a standard transformer for vision. The more layers, the better, like a rule of thumb, kind of. Not always true. And for the text encoder, we're going to use only open source models. So there's no fancy GPT 4.0 or whatever, O2 or whatever new thing they have. We're just going to use very simple language models like BERT and Roberta to do this. And our baselines are going to be, whatever people were using before. So a lot of like risk insurance, we're using XGBoost for these. And the rest of it is just to have a comparison for only vision models. Okay, so this is how it looks. We're going to use the F1 weighted score. This is, you can read it as accuracy as like 1 being like you're predicting everything, and 0.5 being like random. So the single vision model is performing better than both our baselines, which is kind of like what we expected. Only text models are predicting a lot more. The reason behind that is because we're giving information about things that we know matter in a fire, right? Like the temperature, the GDP, how much precip there was the month before, things like that. Like, so those features are very informative. So this is kind of like non-surprising to us. But what happened if we combine both? And this is where this gets very exciting. Is that these double encoding models are giving us like a high bump in prediction. And the reason of that is like we are able to combine these two things, and like so activations within these models are changing. And on top of that, we're only using 1% of our labels. So these models in green are only seeing 1% of the labels. So what is happening here? So basically, this is our only vision model. This is just like one random attention head that we're getting here. So this is only one attention map in the transformer. We can see some defensible space just counting the number of pixels. But when you see vision and text, you see like there is something more that is happening here. You see like a little bit of the defensible space can be explaining this, but at the same time, weather and other features can be changing this. Now, there is a problem with this, is that we cannot interpret activation functions as causal. So that's one. And two, is very complicated sometimes to interpret like what these activations are telling us. And that's a little bit of what I'm going to talk about in the second part of this. Okay, this was classification. This seems like pretty easy, but can we think of something similar for a harder task? So basically what we had in the complete architecture is called the encoder-decoder architecture. And what we were using was only this like purple part in which we have our data, and we just want to take it into a smaller embedding space, and that's it. But the complete model, it's usually what you see on a UNet, in which you have like you have some data, you are trying to reconstruct the data. So you have this function, this f dot, that is like basically doing that. It's like our reconstruction, using a reconstruction loss. So it's basically creating this embedding that is very smaller than our data, and it's trying to reconstruct our data and then put it in like in the tilde space. That's kind of like what these models are doing. And this f dot, a way of interpreting this is just like you have like a vector representing your data. It's representing not only the space, it can also represent the time, it can represent different features. And this is like up to you. So basically a lot of these models, the hypertuning comes from what are the best parameters that I can pick to represent my data into this. And this is a very exciting part of the new kind of like weather ML literature, in which a lot of the things that you see that are happening on these papers is exactly taking different levels of the atmosphere, different variables of the atmosphere, and trying to summarize them and trying to understand what's happening within them. So, for instance, ML, this is like GraphCast. So GraphCast is using a similar architecture to pass this to the actual graph model. Pangu Weather is doing the same. So it's like they're trying to build like the best small embedding representation. This is kind of like similar to what we used to do before, in which we do like PCA or EOFs to capture like physical phenomena. And the power of these like autoencoders is that we're able to have like more complex representations that can take not only a space and like variables, but also time. So we can use kind of like my pitch here is that we can use these low dimensional embeddings to learn physics or chemistry and also to learn faster. So this is an example of a paper that is trying to do precipitation modeling. And one of the problems in the tropics is that you are going to have like microphysics that you cannot understand because they're like subgrid phenomena. And at the same time, you have a bunch of parameterizations. You usually have to run these models, and these parameterizations are usually very bad. So what this paper wants to do is like, how can we build better parameterizations? So they're going to run a bunch of simulations. They're going to have a coarse level, like a coarser representation, like a resolution of them, and then like a high resolution. And what they want to do here is that they want to learn this ORG. This stands for organization. That's kind of like the structure, the organization of the clouds across levels, but also across a space. And this is something that in the past, the parameterization just like decides like, oh, like geometrical features or geometrical like descriptions of these, and they pass those parameters into the model. So this is kind of like the first time that we do these like with data. And as I was showing before, basically what you want, what you care about, you don't care about decoding this. Like, I don't care if it's like reconstructed the real data. I only care about like this small embedding. And what this small embedding is doing is like, we can pass this as a feature with our large scale. Like those are the low resolution ones. So we can like pass what we learn, the physics, what we learn. This is, we're gonna see how those physics look like later, and my data, and I can use these as inputs for a new model. And what this paper shows basically is like, it increase your R squared by a lot. So I think only using no org, like only using large scale, which is their baseline, is like R squared is like 0.5 or something. And then it jumps to 0.92, which is pretty good for tropic precipitation, in the tropics. Now, this resembles a little bit my comment with the burning, or like what's happening in these embeddings is like, you have no clue what's going on. So you will have these embeddings, they can have like a lot of years, a lot of like days or months, and a bunch of variables and different parts of the world. And they can be like any size. So in this paper, the authors were playing around with like 2, 4, 8, which is kind of like the standard size for like the width of your of that matrix. But sometimes you don't know what to interpret from this. So when I was reading this paper, it's kind of like, huh, interesting. I don't see anything there. But they try to make something out of it, and they try to understand what are the faces. You can run a Hofmuller plot, so you can see what is the face of the clouds parameters they're trying to get, and try to check if this is really capturing the physics, what we know that they exist in this part of the world. So one caveat here, of course, is that the more, the higher this embedding space is, kind of it's defeating the purpose a little bit, because then you're learning just your data. So you want to keep like your dimensions small enough to be tractable, but also like big enough that they can have a good reconstruction error. This is like a very active space still. Like at Stanford, there's like different labs like Hazy Research, and the whole thing is trying to understand the kind of like the linguistic properties of language. And this is still a thing that no one has understood yet. Like, these language models behave well, sure, are they reconstructing linguistical patterns? It's something that like people are trying to still get into the model and see like, oh, can I found these in these models? And this paper, Burns is trying to do that. Um, and of course, one of the things here is like, if our data is bad, then we're gonna clearly have like bad representations of the world, like bad physics. And this comes just from like biases. So these Buluk-Basi paper is like a famous one in which they found that like large language models are, or like at the time, like those language models were like gender based, which is comes to no surprise to anyone. They're trained on data that we are like, they're trained on Reddit posts. So, you're gonna get what you train with. Another promising part of this is, can we learn faster? And this is something that it's very exciting from my POV, in which okay, this is coming from a paper called Satme, and can we use, rather than starting pre-training from scratch, can we fine-tune things that are already on the wild? And this is something that is like widely practiced in computer vision. This is an example from one of my advisor's papers, in which they're building using models that were already pre-trained. They're going to create a new fine-tuning process that is using a birational autoencoder that is basically just masking the data. I cannot see, I don't know if you can see my pointer, but like there is like this mask input, there's a temporal input, there's the mask input, and then the reconstruction. So the reconstruction is like what we had at the end of our architecture, what I told you guys not to care about. But in this case, we care about. And what is happening in the middle is that we're masking patches. So we're asking our net to just like fill the gaps of that. And the reconstruction is giving us that. So basically what is sexy about this model is like, this is the first paper kind of that like use this way of training to fill things. So basically, in this case, there is no physics, there's nothing, but what the embedding is learning is like learning how to fill those gaps. And it's doing this through time. So when you're asking it to reconstruct, you're only giving the input from the first time, with time 0 in the first cell. So it's able to capture time. So the whole thing of this paper is like, oh, we can use things in the present right now to learn how things are going to change in the future, given what we have learned. And we only need this low embedding representation from like auto models. So this is what made like this paper very powerful. And this is kind of like the first building block from like more complex models um, um, for more complex models. So these, we can learn like these semantic encodings. There's like a different flavor of models like this, in which you can like learn, like, I don't know, if you look for plane, then the model is gonna search along the embedding, and it's gonna search the representation of a plane, and you can get all the planes in the images. That's how like that's how search will work on this. This has a name in language called RAG, retrieval augmented generation. And a thing that we learned from this paper is that a good representation, a good low embedding representation, is able to represent data and the laws. In this case, like the physics laws, as we saw in the precipitation paper. But it's also able to fine tune these features into new data. So one question here, and this, I brought this paper. This is from the Aurora paper. This is Aurora is like one of the foundation models from Microsoft Research. And one cool thing they do here is that the model is not seeing pollution. So the model is only training on ERA 5, all the usual suspects. It has some satellite imagery, but it doesn't have pollution, or it doesn't have like any measure of like atmospheric chemistry. And what they're trying to see is the model, can I train Aurora to another task? In this case, forecasting nitrogen. I think it's nitrogen. I don't know chemistry, don't judge me. But basically, the cool thing here is that the model is not seeing these things. I'm gonna show them for the first time. I'm just gonna one-shot pre-train it. So I'm gonna only show. Sorry, this is like one shot. Yeah, I'm only gonna show it an example, and then I'm gonna let the model do the rest. The show is like, this model is good at the analysis. Is better, is performing better. So that's kind of like very telling on a way of like, how can we fine tune and how can we use these like vast models to basically fine tune them to a singular task. And this is the case for Aurora. Aurora has their weights are available. Uh, I haven't tried it, but there's like other smaller foundation models, quote unquote, like arches. Um, and there is clay, but clay doesn't work well still with climate data, but clay is good for like the upper example of like satellite imagery. Okay, cool. Yeah, and all of this was thanks to open source models and my university cluster. Yeah, that's all for me.